Good morning, everyone. Today we continue with our module of engineering physics, unit 2 of oscillations. Most of material in this part deal with simple harmonic motion. Many objects vibrate or oscillate, such as the object on the end of a spring, the tuning fork, a balance wheel of an old watch, a ruler held firmly over the edge of a table and gently struck, the strings of a guitar or piano. Cars oscillate up and down when they hit a bump. Buildings and bridges vibrate when heavy trucks pass or the wind is fierce. The oscillations of a block attached to a spring. The swinging of a child on a playground swing. The motion of a pendulum. The vibrations of a stringed musical instrument, and so on. Starting with simple harmonic motion, let us consider an object attached to a spring when the spring has its original length. We say that the extension x is equal to 0. And then we may pull the spring with this body of mass m. Once we pull the spring is extended by an extension or a displacement x. Then there is a force on the spring, which is called the restoring force F. This restoring force is a force which makes the spring to tend to retain its original length. Then when stretching the spring, we stretch it to the right, and the spring force is oriented to the left. The third case is when we compress the spring with the same mass. By compressing the spring is compressed at a displacement x, or a length x, which is negative. Then the spring force is a force which allows the spring to tend to retain its original length or shape and size. Then it is oriented to the right because the compressing force is to the left. Then when an object vibrates or oscillates back and forth over the same path, each oscillation taking the same amount of time, the motion is periodic motion or harmonic motion or oscillation or a vibration. And here there is a position that we call equilibrium position. This is the position of the mass when the spring has a natural length, means its original length. Then the restoring force is expressed by the Hooke's law. This force equals 2 minus kx, where k is called the spring constant or the force constant, and the x is the displacement, either extended length or compressed length. The minus sign here indicates that the restoring force is always in the direction opposite to the displacement. When you stretch the spring, the restoring force is in the opposite side to the left. When you are compressing the spring to the left, the restoring force is to the right, as shown here. Here we have a spring with its natural length. Once you attach an object of mass m to the spring will be extended, and the extending force is the weight of the body, the gravitational force mg, and the restoring force is a force oriented upward, F equals minus kx0. x0 is the maximum extended length of the spring. Then here, when the equilibrium is reached, the new equilibrium, this spring force is equal to the stretching force, where we deduce that the sum of forces is equal to 0 at equilibrium. Here we apply Newton's first law. When a body stops from moving, or it is not moving at all, or when the body is moving with a constant speed along a straight line, the sum of forces acting on it is equal to 0. Then the body in the spring moves downward. Then this weight mg is positive, while this force in the spring is negative, upward, minus kx equal to 0. Then mg equals kx0. We have then mg is equal to kx0. x0 is the maximum compressed or extended length. Then here we may determine k as the spring constant, which is equal to mg divided by x0. This means that the spring constant k is equal to the applied force divided by extension. It means this is equal to the applied force divided by the extension or the compression distance. Then an object moves with simple harmonic motion whenever its acceleration is proportional to its displacement. Here in this equation, you see that the acceleration is directly proportional to the displacement. Then here comes the equation of motion. Then a simple harmonic motion is characterized by what we call amplitude of simple harmonic motion, period of simple harmonic motion, frequency, and angular frequency. The displacement is the distance x that the mass from equilibrium position makes, and the amplitude a is the greatest distance from equilibrium point, and the period is the time taken by the oscillating body to complete one revolution or one cycle. Then it means a time taken to make a full cycle. And we know here a complete cycle or a complete oscillation or a complete vibration is a round trip, which means that when a body moves from positive A to negative A and back to positive A. And the frequency F is the inverse of the period, which means that the number of cycles per unit time. Here, mathematically, the frequency is equal inverse of the period t. T is inverse of the frequency. And the angular frequency is 2 pi times the frequency, means 2 pi over t. Example number 1. When a family of 4 with a total mass of 2,200 kilograms step into their 1,200 kilogram car, the car spring compresses 3 centimeters. We are given x equals 3 centimeters. X is negative because there is compression. The mass which compresses the spring is 200 kilograms. So the compressing force is equal to the weight, 200 kilograms times g. G equals 9.8 meters per second squared. And we have the compressing force, 1,960 newtons. And this force causes a compression of 3 centimeters, means 3 times 10 to the power minus 2 meters. So we are asked to determine the spring constant K. The spring constant K is equal to the compressing or extending force divided by extension or compression. Then the spring constant equals to the weight of the 4 people, 1,960 newtons, divided by the compressed distance, 3 times 10 to the power minus 2 meters, which is equal to 6.5 times 10 to the power 4 newton per meter. Then B, how far will car lower if loaded with 300 kilograms rather than 200 kilograms? Now we have obtained the spring constant K in a normal condition. Now we are asked to determine the compressed distance or the compressed length if the force changes. The force changes to a new force of 300 kg times 9.8 meter per second squared, then divided by the calculated spring constant of 6.5 times 10 to the power 4 Newton per meter. This gives 4.5 times 10 is 10 to the power minus 2 meter, or 4.5 centimeters. Then example 2, an ultrasonic transducer used for medical diagnosis oscillates at a frequency of 6.7 times 10 to the power 6 Hertz. How long does each oscillation take? An oscillation, a complete oscillation, takes a time which is equal to the period t. Then, and what is the angular frequency? We are asked to determine the period t. The period is equal to the inverse of the frequency. So this is equal to 1 divided by 6.7 times 10 to the power 6 Hertz, which is equal to 1.5 times 10 to the power minus 7 seconds. And the angular frequency equals to pi f equals to pi. Pi is equal to 3.14. You know it. Pi is equal to 3.14. Then we will obtain that the angular frequency omega equals 4.2 times 10 to the power 7 radian per second. This is a very rapid vibration because the time taken for one complete oscillation is very small, 0.15 microsecond. Then if the period is very small, the vibration is very quick or very rapid. Then if the period is very large, so the vibration is not rapid, is slowing down. Then we start with the equation of motion for the simple harmonic motion. We start if a body is in motion, the sum of forces acting on the body is equal to the mass times the acceleration. We know that the acceleration is equal to the second derivative of position with respect to the time. And the sum of forces acting on the spring, which is the spring force, means the restoring force equals minus kx. If we put this on the same side, we have d squared x over dt squared plus k over mx equal to 0. This is a second order differential equation whose answer gives that x equals a cosine omega t plus phi. Here A is the amplitude of oscillation. The amplitude of the simple harmonic motion is the maximum stretched or the maximum compressed length. And the omega is the angular frequency and phi is the phase angle. Here we see that this displacement changes sinusoidally as the time flies. Then the equation of motion here states that x equals the amplitude cosine omega t plus phi is the displacement. If you have a displacement, you can determine the velocity. We know that the velocity is equal to the first derivative of this position with respect to the time, equals d over dt of a cosine omega t plus phi, and the derivative of a cosine or sinusoidal function, derivative of cosine gives minus sine. Then this omega will come to multiply a. So then we have minus omega a sine omega t plus phi. Second derivative gives derivative of minus omega a sine omega t. Derivative of sine gives cosine, and this omega will come to multiply minus omega a, where we have the second derivative of x with respect to the time equals minus omega a squared a cosine omega t plus phi. This is acceleration, and the first derivative is velocity. If we want to put this the second derivative and the x in the first equation, means in our second order differential equation, we get a new relationship between the angular frequency, spring constant, and the mass, where we have omega squared equals k over m, or for the simple harmonic motion, the angular frequency equals to the square root of k over m. And then in summary, for simple harmonic motion, the frequency equals omega over 2 pi equals 1 over 2 pi times square root of k over m, because omega equals square root of k over m. And the period, which is equal to inverse of the frequency, equals 2 pi over omega, which is equal to 2 pi times the square root of m over k, inverse of omega. And then displacement is a function of time, x equals a cosine omega t plus phi. And the velocity in a simple harmonic motion, which is equal to the first derivative of position with respect to the time, equals minus omega a sine omega t plus phi. Here, this amplitude is the maximum value of displacement. And omega a minus omega a is the maximum value of velocity. And acceleration is the first derivative of velocity with respect to the time, which is equal to minus omega squared a cosine omega t plus phi, where the maximum acceleration is minus omega a minus omega squared a times a. And here we have velocity is a function of time and acceleration is a function of time. Then the maximum velocity omega a, omega is equal to square root of k over m, 10 times a, and the maximum acceleration equals omega squared a, which is equal to k over m times amplitude a. Then this is the variation of x. X varies between minus a and plus a, where velocity varies between minus maximum velocity, means from minimum velocity to the maximum velocity, and the acceleration varies between minimum acceleration to the maximum acceleration. And here we have some important properties of a particle in simple harmonic motion. First one, the acceleration of a particle in simple harmonic motion is proportional to the displacement, but in the opposite direction. Secondly, the displacement from equilibrium position, velocity and acceleration all vary sinusoidally with the time, but not in phase. Then the last one, the frequency and the period are independent of the amplitude. Here, don't confuse the frequency f and the angular frequency omega. The frequency f means the number of cycles or number of oscillations per unit time, while angular frequency omega is the number of radians per unit time, means how many radians were moved per second or per unit time. Then energy in simple harmonic motion. Here, when the spring is compressed, it is at a position minus a, means the negative of amplitude. So the velocity is equal to 0. When the velocity is equal to 0, the body doesn't have kinetic energy. The kinetic energy is equal to 0. And the position is minimum. Once the position is minimum, the potential energy is maximum, because we know the potential energy is elastic potential energy, which is equal to the half of kx squared, as you learned it this in classical mechanics. Then here x is equal to minus a. So we have a maximum potential energy when a body is at minus a. And when a body is at equilibrium position together with the spring, the velocity is maximum at equilibrium position, but x is equal to 0. When the position is equal to 0, the potential energy is equal to 0, and the kinetic energy is maximum. It's the reason why the mechanical energy is equal to the maximum kinetic energy. And when the body and the spring oscillate and reach the position of x equals a, maximum amplitude, the velocity is equal to 0, then the kinetic energy equal to 0, and the x equals a, so the potential energy is maximum, and the mechanical energy E is equal to the maximum potential energy. And when a body is between the equilibrium position and the amplitude, the mechanical energy is equal to the kinetic energy plus potential energy. Where we have the total mechanical energy is equal to the sum of kinetic energy and the potential energy. Here, the kinetic energy is equal to the half of mass and the square of the speed. The speed equals 1 over 2 m. Speed is omega a, then omega squared a squared sine square omega t plus phi. Potential energy equals 1 over 2 kx squared, which is equal to 1 over 2 k a squared cosine squared omega t plus phi. If we add the potential energy, kinetic energy, we will find that the total mechanical energy equals 1 over 2 times the product of spring constant and the square of amplitude. Then, which means that the total mechanical energy is a constant because the spring constant is a constant and the amplitude is a constant. This diagram shows how potential energy varies. At minus a, the potential energy is maximum. When x is equal to 0, the potential energy is equal to 0. And when x equals to a, the potential energy is maximum. And the total mechanical energy, which is equal to the sum of potential energy and the kinetic energy, is equal 1 over 2 ka squared, which is a constant. Then this diagram shows how time, x, position, velocity, acceleration, kinetic energy, and the potential energy varies respectively. Then applications of simple harmonic motion. On the first one is the vertical simple harmonic motion, which is similar to the previous one. When a spring is attached to the body will stretch the spring, and then the spring will tend to retain its original length. Then at some time, the spring together with the attached body will reach equilibrium, where the force in the spring is equal to the acting force. The second one is simple pendulum. Simple pendulum. A simple pendulum is an oscillation which consists of a small object, which is the pendulum bob, that is suspended from one end of the lightweight cord, as shown in this diagram. Then there is a vertical support, and we take a chain or a cord or a string, and then which is fixed to the support, and there is a free end as shown in this diagram. We have this vertical support, then we take a string of length L, and to the free end we attach a cord, and then we let the cord and a body of mass M to move an angular displacement theta. And here, this is where the motion starts. If we release this body of mass m, it will move back and forth. While moving back and forth, it makes oscillations similar to the simple harmonic motion. And here, the force which makes the body to move is its weight. It means the force of gravity mg, which makes an angle theta with this axis. And then this mg sin theta is the force which is oriented in the direction of motion, but in negative x. And the mg cosine theta oriented towards this the string. Then here the force equals that is acting on a body is called minus mg sin theta. Then for very small angles, sin theta is equal to theta, because these angles are expressed in radians, not in degrees. It means angles less than 15 degrees. Then the sin theta is approximately equal to theta. It's the reason why the force equals mg theta. And this x is equal to L theta. Means sin theta would be equal to opposite side is x divided by hypotenuse. Hypotenuse is equal to the length L. Then x is equal to L theta. Then theta equals x over L. So we have this force acting on this bulb is equal to mgx over L. If we equal this force with mass times the acceleration and input it into the equation of motion for simple harmonic motion, we will see that the angular frequency of the simple pendulum is equal to square root of k over m equals square root of mg over L divided by m, which is equal to the square root of g over L. Then this omega is equal to square root of g over L, which is where g is the acceleration due to gravity and L is the length of the pendulum, means the length of the cord used to form this simple pendulum. And the frequency, which is equal to omega, means the angular frequency divided by 2, is equal to 1 over 2 pi times the square root of g over L. And the period, which is equal to the inverse of the frequency, equals 2 pi over omega, equals 2 pi times the square root of L over g. And another application of simple harmonic motion is the physical pendulum and the torsion pendulum. A physical pendulum is a rotating rod, where we have a rod may rotate at the center of gravity, meaning at the center of mass. This rod rotates because of its weight, mg. Then once the body rotates, it makes back and forth more motion. And then the torque is the cause of motion is equal to minus mg h sin theta, where we obtain the equation of motion for a physical pendulum given by this equation. And then the angular frequency for a physical pendulum is equal to the square root of mgh over I. I is the moment of inertia, m mass, g acceleration due to gravity, h the height at which the pendulum is, and then the period, which is equal to 2 pi over omega equals 2 pi times square root of I over mgh. And here we have an example of calculation. Let us consider a uniform rod with length L equals 1 meter, which is pivoted at one end, means here is an axis of rotation at this point. Then as shown in this figure, what is the period of the motion? Take g equals 9.8 meter per second squared. The length of the pivot, the length of the rod is 1 meter. The pivot means the axis of rotation, it is 1 meter. Then here we have the center of mass, and then the center of mass, we need to find the period equals t equals 2 pi of times the moment of inertia over mgh. Then h is equal to the length of the distance from the axis of rotation to one end to the center of mass. Then this is equal to 2 pi times the square root of 1 over 3 ml squared. 1 over 3 ml squared is the moment of inertia of a uniform rod when an axis of rotation it is at one edge, divided by mg. H equals L over 2, because h is the distance from the center of mass to one end, it means to the axis of rotation, which is the half of the total length. Then we will have the period equals 1.64 seconds. The torsion pendulum is also a rotating disc which is connected to a string that is fixed at one end to a vertical support. Then once this disc is rotating, it makes oscillations, which is called a torsion pendulum, and the torque is the cause of the rotation. This torque is equal to minus k theta, where theta is the angle that can be elapsed by a particle on the rim of the disc. Then the second, damped harmonic motion. A damped harmonic motion is a harmonic motion which has friction force or a drag force in during the oscillation. This means that the amplitude of the oscillation decreases sinusoidally with time. Means the amplitude is decaying as the time flies. Means the amplitude becomes smaller and smaller. This is due to air or fluid resistances. And when there is damping, the equation of motion becomes complicated. It becomes the exponential function as shown in this equation, where the displacement xt is equal to amplitude times e to power minus b over 2mt, where b is a damping coefficient times cosine omega t plus phase angle. This b is what you call the damping coefficient. Then there are types of damping. There is what you call light damping, means small damping, when the damping coefficient is very small. There is what you call heavy damping. For heavy damping, there is a large damping factor. And there is a critical damping, which is done in 1 second. Means that k over m means omega squared equals b squared over 4m squared. Then for light damping, which is actually called under damping, there are a few small oscillations before the oscillation starts to rest or comes to rest. Then for heavy damping or over damping, the system is slowed so much that it takes a long time to get equilibrium. Then for a critical damping, this is a very fast way to get equilibrium. Then this is the fastest way to get the equilibrium position. And this damping has an effect on oscillating system. The first effect of damping on oscillating system is a decrease in amplitude of the oscillation. The second, a decrease in frequency, means increase in period of the oscillation. That you must know these effects of damping on oscillating system. The first, decrease in amplitude of the oscillating system. Second, a decrease in frequency, means increase in period of the oscillation. Then number 3, forced oscillations and resonance. A forced oscillation is an oscillation with a driving force. Means when we need to push the oscillation until we reach the peak frequency. This is especially done for musical oscillations, especially for musical instruments, TV and radio receivers, because we need to capture the maximum or to emit the maximum frequency that everyone can receive. Then so we need to change the frequency to the maximum frequency that can be obtained. Then when an oscillation has a force, means that we have a forced oscillation, the amplitude changes exponentially, and the equation of motion is a second order differential equation as shown in this equation. Then if there is resonance, the damping factor becomes very small, and then the frequency becomes very, very high for resonance. And this is the end of oscillation. We will follow with exercises and then mechanical waves. Thank you for watching.